So Anna, did you get any snow?
So I'm in Newfoundland.
She's in town,
actually.
yeah.
Oh, you're actually in
Yeah.
I'm
Oh,
very close to all of you right now, probably.
Oh,
It was snowing in Toronto last night.
I did receive several pictures from friends who were like, "Oh my God, there's like an inch on the ground," and I'm
shocked,
like,
right?
"Okay."
However, when was the last time in April when there was snow on the ground in Toronto and not in St. John?
Yeah, I was pretty surprised. There is still like a tiny patch. There's a tree line near us, and there is a little bit of snow still left. So we're almost there.
I think we're doing well.
Who remembers Star Party in Anna's potato field?
Well, I don't know if it was a star party. I remember having a telescope there.
Yeah.
Hello, everybody. Welcome to the Royal Astronomical Society St. John Center. I'm your president. It's nice to see so many familiar faces again, and we've got a great speaker tonight. Every time she comes, she just blows my mind, and it's really interesting right now because I thought it was interesting that she was doing some other research, and her research helped her find something else, which just blows me away. I think we have enough members to start the meeting. Do we, Randy? You can ask questions under the chat because I don't see a question and answer thing down there tonight. So if you have any questions, I would assume she'd like the questions. I'd like to introduce Mike to introduce our speaker for tonight. We're going to go right directly into our speaker because I'm afraid we might get knocked out, although nobody is scheduled to be on tonight.
Okay.
All right. Go ahead, Mike.
So it's a great pleasure to introduce Anna O'Grady. She's an astronomer she's well known to a lot of us. She got her BSc honors in physics and applied math at Memorial, and she's a PhD candidate now at the Dunlap Institute at the University of Toronto. She studies evolved massive stars, which are stars that are giants or supergiants. They're past the stage of burning hydrogen in their cores, and also supernova progenitors. And 2 years ago, she told us about some of the objects that she searches for, and one of them was Thorne-Zhitkov objects, which had been hypothesized. These are giant stars, red giants, that have engulfed a neutron star. And a few weeks ago, there was some of us saw a press release from the Dunlap Institute about a discovery that Anna had made in the course of her research. And she discovered about a dozen very special stars out of, I think, probably more than 1 million, but she'll tell us about that, that are at the boundary between massive stars that are going to be supernovas and less massive stars that are going to end up as white dwarfs. And this is the kind of discovery, I think, that ends up in textbooks. And so it's pretty important. And I think we're very lucky that Anna agreed on very short notice to tell us about her discovery tonight. So Anna, thank you very much, and take it away.
Awesome. Thank you so much, Mike, and for the invitation and the amazing welcome. And thank you to the Rask Center in general for the invitation. I'm super, super happy to speak to you all. I have a great time when I present here. And yeah, I'll just get my screen shared right now. And can everyone see that?
I can.
Yep.
Okay. Great, and I'm just going to pull up the chat here. So yeah, if anyone has any questions, feel free to ask in the chat. I can see it, and I'll answer questions as the talk goes on, as well as at the end. So yeah, oops, okay. To start us off, as some of you probably remember, I previously gave a talk to you 2 years ago on Thorne-Zhikov objects, which are a really fascinating class of massive stars that are red supergiants with neutron stars inside of them. So they are literally stars within stars, which is absolutely fascinating. And I spoke to you about a population of stars in a nearby galaxy that I thought might be Thorne-Zhikov objects. So this is what my talk looked like when I spoke to you 2 years ago. Now, when I speak on this topic, this is what my title slide looks like. So you might be wondering, how did that happen? And was I expecting this? And I will walk you through the journey, starting broadly, but I'll walk you through the journey of how I ended up at this very, very different place than I was initially expecting in my research. So first I'll explain why were we looking for Thorne-Zhikov objects, or TZOs, in the first place. So beginning broadly, my research focuses on stars. The stars that we can see in the night sky and those that we cannot, those that are farther away. Stars are, of course, the fundamental building blocks of our universe. They're the contents of our galaxies and the hosts to our planets. Lots of different types of stars exist, some more common than others, and studying stellar populations as a whole gives us a wealth of information about our own universe. So when we take the stars that we can see in the sky, whether they be in a cluster or all of the stars that we could possibly identify in a galaxy, and we organize them by their brightness and their temperature, we can construct a particular type of diagram called a Hertzsprung-Russell diagram. So this is an example of a Hertzsprung-Russell diagram. So on the vertical axis here, we have the brightness of the star in how many times brighter than the sun it is. On the horizontal axis here, we have the surface temperature of the star, with very, very hot blue stars on the left and colder red stars on the right. You can see our sun right here, and that is on a feature that is known as the main sequence. So the vast majority of stars spend the vast majority of their lives on the main sequence, burning the hydrogen in their core into helium in order to support their outer envelopes. Stars like our own sun, once they run out of hydrogen, they will ascend something called the giant branch, and later the asymptotic giant branch. So they will swell up into these really, really huge red giant stars and become very cool. And the reason that's called the asymptotic giant branch is because the actual evolutionary path in this diagram that these stars take go really vertical in this section. So it's like an asymptote to the graph. On the other hand, for stars that are much more massive than our sun, so stars that are sort of up in this area, when they evolve off the main sequence, they become supergiants. So these are absolutely massive stars in their radius and also in their mass or weight. And these are the stars that will eventually explode as supernova explosions. So my main focus of research is on supergiants, but making sure that we have a broad understanding of multiple different types of stellar populations is really important. So studying broad populations of stars is important, but also crucial is studying unusual or rare stars. These types of stars can give us insight into strange physics or very short-lived phases of stellar evolution. And one example of a really unusual star is HV2112. It's located in the small Magellanic Cloud, so one of the satellite galaxies of our Milky Way that you can see in the southern hemisphere. It's actually in this image. It's this one, that little star right there. So yeah, the star looks unassuming in this massive star field, but the true nature of the star has actually been hotly debated over the years. So in 2014, HV2112 was the very first identified candidate Thornjikov object. Now, TZOs are a really, really strange class of red supergiants. So they're classified as a massive star, but unlike normal red supergiants that have a core made of degenerate elements like helium and carbon and oxygen and neon, Thornjikov objects have neutron stars inside of them, where the neutron star is the remnant of another star that exploded as a supernova. So how do you even have that happen? Well, to create a TZO, you have to have a binary system where you have two massive stars orbiting each other. One is a little bit more massive and it runs out of fuel faster. So it will explode as a supernova first, leaving behind a neutron star. And then either through the process of common envelope evolution or by the supernova itself kicking the neutron star into its companion, the neutron star can enter the envelope of the other red supergiant, merge with the core, and then you have a Thornjikov object. So these are theoretical objects. Kip Thorne and Anna Zhikov worked on the physics of these in the 1970s, and they worked out many of the properties that you expect to see in TZOs, and very specifically, they asked the question of stability. Are these stars stable? Can they actually exist? And they found that TZOs should be stable as long as they are larger than 15 solar masses. So 15 times the mass of our own sun. If they're above that, we're good. Stars like that can exist. And figuring out if TZOs exist is extraordinarily important, especially in terms of figuring out how many binary systems could end up like this instead of a different type of merger scenario. You could imagine another type of scenario is if the neutron star does not merge with its companion, that companion creates another neutron star, and then you get something like the neutron star merger that we saw a few years ago. So understanding the relative ratio between systems that might go like that versus systems that turn into TZOs is really important for understanding the content of our universe. So from a photometric perspective, so just looking at discrete wavelengths of light with filters like the ones you might use on your telescopes, TZOs are predicted to look a lot like normal red supergiants, making them hard to find. They'll be very luminous and very red. They'll look a lot like Betelgeuse, one of the brightest stars that we can see in our sky. However, in the extremely hot atmosphere of the neutron star at the center of a TZO, the extremely hot atmosphere can allow a particular type of nucleosynthesis to happen to create very rare elements that you do not see in a normal red supergiant. And that is how Emily Levesque identified HV2112 as a TZO candidate. She and her team found that it possessed these rare types of elements. However, as I mentioned before, the nature of HV2112 has been debated. Other studies have actually found that its properties are much more similar to that of a super AGB star. So what are those and how are they different? So going back to our picture of the evolution of stars after they leave the main sequence, low mass stars, like our own sun, will eventually leave behind white dwarfs made of either helium or carbon and oxygen, depending on the mass of the star. Massive stars, on the other hand, will explode as iron core collapse supernovae and leave behind either a neutron star or a black hole. But then where is the divide between low mass does not explode and high mass does explode? How big does a star need to be to get to the point where it suddenly starts to explode as a supernova? That regime is what we call super AGB stars. So some of these, the slightly less massive super AGBs, are thought to leave behind an even more complex white dwarf with oxygen, neon, and magnesium. This is because the super AGB star is big enough that it can proceed to higher stages of nuclear burning than a smaller star, whereas the most massive super AGB stars can explode as something called an electron capture supernova. So within this regime is literally the tipping point between something that'll make a white dwarf and something that will make a supernova. So about 8 solar masses is typically said to be the canonical dividing line between stars that do not and do explode. And we know that super AGB stars exist, but the exact masses aren't really well constrained. It depends on a lot of things, like the types of evolutionary models you're using, how you handle convection in the star, metallicity. The general range is thought to be at the low end from 6 to 7 solar masses to about 10 to 11, maybe 12 solar masses at the high end. And at the time that I started this project, there was only one candidate super AGB star. It's in our own galaxy. So if someone found more of these, it would go a really long way towards understanding what stars do and don't explode as supernova. Unfortunately, and the reason why there's a debate about HV2112, TZOs and super AGB stars share a lot of similar properties. They're both very cool, red, luminous stars. You would expect super AGBs to be a little bit less luminous because they're giants and not supergiant stars. But getting extremely accurate measurements of the brightness or luminosity of stars, especially at the distance of the Magellanic Clouds and having to correct for things like dust in the line of sight, it's really difficult. So HV2112 is right in this sort of uncertain area of, is it bright enough to be a TZO, or is it not quite as bright, making it more likely to be a super AGB star? So this is the problem. HV2112 has similarities to both Thorne-Zhikov objects and super AGB stars, both fascinating objects, and it would make a big deal if HV2112 was either of these. But which one is it? So when I started this project, with the caveat that my hypothesis going into this was that HV2112 was a Thorne-Zhikov object, and we'll see how that turned out as the talk goes on. There were 3 main problems that myself and my collaborators approached this with, or 3 questions. The first is HV2112 unique, or are there other stars with similar properties? This first question is super crucial because no matter the true identity of HV2112, if it's a TZO or super AGB or something else entirely, knowing if there's 1 of those or 10 of those or 100 of those is very important to understanding the occurrence rate and the possible origins of these stars. The second question is there a population? And if there is a population, how does it compare to other common stellar populations? Is it more like a giant star, or is it more like a supergiant star? And finally, what constraints can we put on the true identity of the population? So is there anything that we can do to try and suss out this question of TZO versus super AGB? So while previous studies, like Emily Levesque's, looked at the elemental abundances in these stars, that is a very slow and expensive way of studying stars. Spectroscopy is really hard. It takes a really long time. So in order to look at a very broad population of stars, we decided to take this from a bit of a different angle and specifically look at the variability of HV2112, or how much its brightness changes over time. And as it turns out, HV2112 is a highly variable star. So this here is the light curve of HV2112. On the vertical axis here is its V-band magnitude. On the horizontal axis is the time in days. And as you can see here, the amplitude of HV2112, so the amount it changes from brightest to dimmest, is 4 magnitudes. That's really big. The period, so the time it takes to go through one variability cycle, is 600 days, so over 1.5 years to get through all of this. And then it has this really interesting double peak feature where it seems like it's getting to the top of its variability and it goes down a little bit, but then it shoots up again, which is a really interesting feature in the light curve. So AGB stars, including super AGBs, can pulsate with this kind of amplitude. Pulsating giant stars like this are called Myra variables. Red supergiants, on the other hand, do not have variability like this. For reference, typical red supergiants vary by about 1 magnitude. So that's the red box that I've put on the screen now, which, as you can see, is way smaller than what HV2112 is up to. However, that's the typical variability of red supergiants. We don't know if the internal structure of a Thorne-Zhikov object, because it is so different from the internal structure of a red supergiant, could be enough to drive larger pulsations in the envelope of the star compared to what you normally see in red supergiants. So the variability by itself is inconclusive as to the identity of HV2112, but if HV2112 is part of a class, we would expect other members of this class to pulsate in a similar way. So we searched the entirety of both Magellanic Clouds, which was millions of stars, to try and find any stars that have the same variability properties as HV2112. And we found them. So there's a whole lot going on in this plot, but the important thing is that there are 12 boxes on this plot, which are 12 unique stars. This one up here on the top left is HV2112, and the blue curve here is the same curve that I was showing you before. And you can see throughout all of these stars, they have high amplitudes, very long periods, and they have this little double peak feature showing up in their light curves. So as I go forward, I'll sometimes show the group of these objects on a plot, and I'll call them HLOs, which is short for HV2112-like objects, because we didn't want to hedge our bets as to which class these might be, so we were safe in the paper, and we just called them HLOs, which is a prescriptive title, but useful nonetheless. So as to the first research question, yes, there are other stars with the same variability properties as HV2112. So this is great. Moving on to the second question, we did several different analyses to compare these stars to other classes of stellar populations. I'll show you a couple of them here. So first, this is a plot comparing the brightness and variability of the HLOs to other classes of stars. So on the vertical axis here, we again have magnitude. This is KS, which is an infrared filter, so redder than our own eyes can see. On the horizontal axis here, we again have the variability amplitude. So how many magnitudes does the star change as it pulsates? The red circles here are pulsating giant stars. So these are all Myra variables. These are kind of like the smaller cousins to the super AGB stars. These are normal or lower mass AGB stars. The violet squares and triangles in the top left here are variable red supergiants. So you can see that they are significantly brighter than the AGB stars. However, as I mentioned before, their variability amplitude is way, way, way less. And HV2112, which I have here in blue, and the HLOs in gold, you can see they're kind of in this middle ground. They have a brightness or a infrared magnitude that is similar to the red supergiants, but their variability amplitude is far more similar to typical Myra variables. So they kind of overlap with both, but they're a little bit more similar to the AGB stars because they do actually overlap with a few of them there. Another analysis that we did was using the photometric properties of the star, like the brightness and the color. We were able to transform that into the physical intrinsic properties of the star and get an estimation of the things like the luminosity and the temperature, which would allow us to construct a Hertzsprung-Russell diagram. So this is a Hertzsprung-Russell diagram like I was showing you before, just with a little bit of a different scale. So this is luminosity on the vertical axis and temperature on the horizontal axis. It's just in log 10 spacing here. And this is essentially zooming in on the top right part of the Hertzsprung-Russell diagram that I showed you before. So the supergiant area is up here, and the giant area is over here. And in particular, these colored lines here are evolutionary tracks made using a code called MESA. And this code solves equations of stellar structure and maps the physical properties of a star of a given mass as it evolves over time. So these green lines on top are for masses corresponding to red supergiants. So this is telling us how a red supergiant of 12 or 15 or 24 solar masses evolves over time in its luminosity and temperature as it evolves towards eventually exploding as a supernova. The blue and violet lines on the bottom are models of high mass AGB stars. And as a reminder, the lower limit for super AGB stars is thought to be around 6 to 7 solar masses. So we're just starting to get into that regime here. The HLOs are over here in this little cornucopia of color. The reason that they're all kind of spread out and not just single points is because as these stars pulsate, they actually change in their luminosity and their temperature. They get brighter and dimmer, they get hotter and colder. So they actually move around a little bit in this diagram, which is interesting. But we can see in general, just the general spot that all of these are located is much more consistent with the very end of the higher mass AGB tracks. They are way colder than you would expect for red supergiants, which is very interesting. So these are the stars in the small Magellanic Cloud. You see a very similar thing for these stars in the large Magellanic Cloud. This is the same, we just have them separated between different galaxies. So this is really interesting. It's again pointing a little bit towards AGB stars instead of red supergiants. However, we do expect Thorne-Zwickau objects to be very, very cold, even compared to red supergiants. So maybe this is expected. And the final question that we had was, is there anything else that we can do to try and find out the true identity of these stars? So answering the second question, they're definitely not red supergiants. But these stars, while they are more similar to asymptotic giant branch stars, what we really want to know is the question of TZO versus super AGB, not just red supergiant versus AGB. And we know that one of the most important differences between TZOs and super AGB stars is the mass. As I mentioned before, TZOs need at least 15 solar masses in order to be stable. If they fall below that, they will collapse, as is said in the theory. Super AGBs, on the other hand, are definitely less massive than that. The exact boundaries of the regime are a little fuzzy, but the maximum theorized mass for a super AGB star is like around 12 solar masses. So they're definitely less massive than Thorne-Zwickau objects. So if we could get an estimate of the mass of these stars, that would be great. However, before we were comparing them to red supergiant models, and we don't have modern models of TZOs to link their luminosity and their temperature and their observed properties to a mass. However, pulsations are often used to constrain the internal structure of stars. And if you know that a star is pulsating, the period or the frequency at which it pulsates can actually tell you about how a star will evolve over time and how massive it is. The MESA code is actually capable of figuring this out. But we do at least have to have a model of the stellar structure. So we need a model of something that has the structure of a Thorne-Zwickau object and can cover the mass range that we expect them to be in, so 15 solar masses and above. And we know that the red supergiant models aren't a great fit, but there is something that we can do here. In order to get a better idea of the masses, one of my collaborators had the idea of making a bit of a simplifying assumption. So Thorne-Zwickau objects have a very, very thick convective envelope of hydrogen and a dense core of degenerate neutrons. that's the neutron star stuck inside the red supergiant. On the other hand, super AGB stars also have a big convective envelope. Their core is a dense core. It's still degenerate material, but it's oxygen, neon, and magnesium, the components that would make up the eventual white dwarf that might be the remnant of a super AGB star. So these aren't exactly the same, but from a really basic structure perspective, both of these classes have big convective envelopes and dense cores of degenerate material. So they're kind of the same at this very like 0th order basic level. So using this, we can use the models of pulsating stars. We can use a model of a pulsating star that has a dense core and a big convective envelope over the full range of masses that we're interested in, from 5 solar masses all the way up past 15 solar masses. And, you know, to a certain level of confidence, this is applicable to both super AGBs and Thorne-Zikov objects. So this is the final plot that I'll show you, and definitely the most important plot that came out of my paper. So here on the vertical axis, again in log space, we have the radius of the stars. On the horizontal axis, we have the period of the stars. So the HLOs all have like 400 to 600 day periods. So that's the sort of scaling that's going on here in log space. So relating the radius and the period together using this model that we came up with, we are able to plot lines of constant mass on this diagram. So each of these colored lines here is a line of constant mass that will describe how, for example, on this lowest mass one here, a 5 solar mass star evolves in both its radius and its pulsation period as it gets older and older and older, because stars expand. And if they pulsate, their pulsation periods actually get longer as they get older. So we also plot the HLOs on here because we have their pulsation periods just from observation, and we're able to estimate the radius. And we can see what masses they're most consistent with. And most importantly, they all, including HV2112, which is this blue one right here, they all fall below the 15 solar mass minimum for Thorne-Zikov objects. So that indicates that these stars are not TZOs. Now, this is with the current theoretical understanding of TZO structure needing to be 15 solar masses. This prediction specifically is sensitive to a lot of complicated physics, and it could definitely change. It could be revised downward, but with our current understanding of Thorne-Zikov object theory, this result points away from a TZO identity. On the other hand, they all mostly fall into the range of masses that we expect for super AGB stars. So when I began this project, this absolutely was not the result that I was expecting at all. But science surprises you in many interesting ways. And the process of going through all of this was definitely a learning experience. And I'm kind of glad that it turned out to be surprising. Mike is asking, are there now no TZO candidates left? So no, there is actually one TZO candidate still. So I would personally say that HV2112 is still possibly a TZO candidate. As you can see, there's multiple things of the points for the radius here, because as these stars pulsate, they actually get bigger and smaller. So if the highest point here is close to the actual correct radius of HV2112, and if the TZO minimum mass is shifted down even a tiny bit, suddenly HV2112 is fine. So HV2112 remains the most interesting star of the bunch. So this, I still think you could say there's still evidence towards it being a Thorne-Zikov object. I just think that the evidence now points more strongly in the direction of a super AGB star. And in one of the papers that debated the TZO nature of HV2112 before mine, it was a 2018 paper by Emma Bizor. they found another star in the small Magellanic Cloud, I think, that also displayed the same chemical enhancements that you would expect a TZO to have. So there is still hope for the TZO cause at the moment. So yeah, so that answers our final question. The constraint that we put with the mass indicates that these are more likely to be super AGB stars, which is really cool. So to just summarize, we identified a population of stars with similar properties of that of the TZO super AGB candidate HV2112. And after some extensive analysis of their physical properties, they seem to be mostly consistent with the predictions for super AGB stars. And while there was one candidate super AGB before I wrote this paper, this would be the first identified population, so a group larger than one. And this is really important for understanding the occurrence rate of these stars, particularly since we looked at all these stars in galaxies that are not our own. You can kind of get a sense of how many of these stars you would expect to see in a whole galaxy, and that can tell you a lot about their overall occurrence rate, which is cool. And in terms of future work on this project, I am still working on some follow-up of an analysis of the spectroscopy. So looking at the elemental abundances of these stars and their physical environments. And just before I end, I definitely want to get to this question. So is it only the largest mass that matters for qualifying as a TZO candidate as opposed to the full mass range or even a portion? That's a great question. I'll just roll back to that. So I would say the full mass range matters. Trying to identify the true radius of a pulsating star is definitely super tricky because as it pulsates, it is actually difficult to understand. Is it only going out in the back end, or is it oscillating around some sort of middle point? So in general, I would take the average of these points to be the true estimate of the radius, but there's always the possibility that the largest point could be the true radius of the star. So yeah, great question. I'll just put up my summary slide again, just if anyone wants to see that, and I'm super happy to take more questions. But thank you very much for the invitation and for listening, and I hope that that made sense, and yeah, thank you.
Thank you very much. I think I'm out. Are there any other questions?
I think one more came into the chat from Phil. Can
Phil.
anything be made of the complex peaks and the double peaks in their light curves? Yes. So the double peak features that you see in the light curves of the star, I'll just bring up HV2112 again. So that is a feature that is seen in some, but not all Myra variables, which are the pulsating AGB stars. And it's thought to actually be shocks propagating through the atmosphere. So I wouldn't say that it's like something that is completely understood, but there is a physical explanation for what might be going on there. So again, this is something that does have a already canonical explanation if these stars are a form of AGB, including super AGB stars. Thank you.
One of the things that you, this is Phil here, one of the things that you have in your illustration, if it has a neutron star core, is neutron stars tend to emit from their poles with streams, whereas the white dwarf, a very complex oxygen, I forget what the elements were, nitrogen and so on, dwarfs don't do that. So that's a direct difference between what we would presume the dense core material to be. If it's one of these very freakazoid objects where it's got a neutron star sitting in the middle, maybe that should make for some kind of observable that would maybe do something like make these shocks. Although you're saying that this is something that's also seen in the Myras.
Yeah, totally. That's a great question and a great observation. So yeah, the existence of the double peak isn't something that we decided to be something against a TZO identity for exactly the reason that you said. We don't have modern models of TZOs, and there is entirely the possibility that the extremely intense environment, the accretion that's happening onto the neutron star, something like that could drive shocks that could create phenomena like this. So yeah, it's definitely still possible.
Is there a characteristic age range for these stars?
For TZOs, yes. They are pretty short-lived. I think 10 to the 5 or 10 to the 6 years. So like 100,000, which is probably a bit lowballing it, to 1,000,000 years, which for stars is fast,
Yeah.
is super fast. Super AGB stars would just be super long-lived. The whole life of that star would be very long in the first place because they're much lower mass. And the super AGB phase itself would, I can't quite remember off the top of my head right now, but we actually did an analysis around this idea of the characteristic age, comparing if we assumed a characteristic age, and then how many of these stars we found in both of the galaxies, do the numbers make sense, basically? And they're okay for both identities, but they're more coherent with the Super AGB identity. So that was another check on the Super AGB column.
That's cool.
Nice talk, Anna. Thank you. Very clear.
Thank you.
I had another question, if that's okay.
Yeah.
So you were mentioning to Phil about shocks being part of the, or maybe being part of the variability. It's very large amplitude variation, and so I'm wondering, is there something exotic about, I think of variable stars as having some sort of valve mechanism involved, and is there something exotic about the valve mechanism here? Is it just because there's such large radius objects anyways that they're very susceptible to, they just naturally have a very large amplitude? Does that make any sense?
Yeah, absolutely. So if these are super AGB stars, then yeah, it would absolutely come down to the natural affinity for these stars to begin pulsating. So common types of variable stars like Cepheid variables, which are a bit hotter, or Myra variables, they start pulsating. They can start pulsating for a variety of reasons. Often it has to do with some sort of change in the interior of the star. If it gets to a certain temperature or a certain density, something like the ionization state might change in the star, and that can drive instabilities that can then grow into pulsations. So Myra variables in general are in an area of the Hertzsprung-Russell diagram that these instabilities can appear, and super AGB stars, even though they're a little bit bigger, they're still in that area. So we would expect this. For Thorne-Zitkov objects, I don't know. I would love for a theoretician or a modeler to make a modern model of a Thorne-Zitkov object and try to get it to pulsate, because I think that would be fascinating, and to try and understand if it does pulsate, what the mechanism is. So that I'm not sure, but I really hope that someone looks into it.
Okay, thanks.
Any other questions, Fran?
And has there been any occurrences of white dwarfs that have any variable nature?
I think so. I forget what they're called, but there are classes of white dwarfs that are variable. They have a particular name of them, so they're a class of variable star that is studied. Yeah, I can't quite remember the name, but there is definitely variability that is seen in white dwarfs. Yeah.
Okay, yeah, well, just thinking that initially in your talk, you mentioned that, you know, the binary system could end up in as one star. And so you could have a white dwarf in the center of red giant, perhaps, and or the neutron star also has the other possibility. But if you had the white dwarf taking up residence in its donor star, and it had a variable nature, then that might drive, you know, the entire system to appear to have a variability. But I doubt that it would be, you know, get to the amplitude as what you have shown there, nonetheless.
No, that's a really great insight, and I think that these are studied objects. Actually, I would need to double check to be sure, but I think there are a type of variable called an R Coronae Borealis variable, which is named after the first star that was found, which is why it's a bit of a mouthful. So they're also called R Core Bor stars, and if I'm not mistaken, those I think are these systems where you have a white dwarf that might be in a common envelope situation with another star, and it propagates a type of variability. So yeah, those objects exist and they're very, very cool.
Not
Do
too
I have one more?
Go
Yep,
ahead.
of course.
So, why are the Magellanic Clouds a good place to look for these? Is it just a favorite spot? I know there's lots of stars there and roughly the same distance, but is there anything else about that makes that a good place to hunt for these things?
Yes, awesome question. So yes, the Magellanic Clouds are an excellent place to do stellar research, and they've become a favorite spot because of that. So as you said, the Magellanic Clouds have a depth to them. They're not like total pancakes, but they're so far away from the Milky Way that you can kind of assume like a central distance, and any error on that won't be super, super, super extreme. So that's a useful thing. The other is that they are really far away from the galactic plane of our own Milky Way galaxy. The galactic plane has a ton of dust that will re-radiate starlight and make stars appear redder than they actually are. There is still some extinction, which is what this effect is. There is still some extinction in the direction of the Magellanic Clouds, but not nearly as much if you were looking towards the plane. So that makes our lives a lot easier. Like I know there's a lot of astronomers in my department who really like dust and love studying dust. I would prefer the dust just get out of the way so I can see my stars. So the Magellanic Clouds make that a little bit easier. They are full and complete galaxies. So if you know that you can see all the stars, you are getting a complete population of a thing that might exist in a galaxy. And that's super interesting unto itself. And the final thing is the metallicity. So the amount of metals, so things other than hydrogen or helium, which astronomers call metals for some reason, that are in a star when it's born. So stars are almost all entirely hydrogen and helium, but there will be a small amount of other elements in that. And the amount of those is called the metallicity. And the Magellanic Cloud has about half the metallicity of our sun in general throughout the stars. The small Magellanic Cloud has about a quarter of the metallicity between our sun. So by comparing the two galaxies, you can see if there's metallicity dependent effects. That's why when I had my Hertzsprung-Russell diagram, there were two separate diagrams. because metallicity can affect the evolution of stars. So you need to have two separate sets of tracks for both galaxies. And then studying the Small Magellanic Cloud in particular, core solar is pretty low metallicity. And when our universe began, stars were just hydrogen and helium and nothing else. And then as big stars exploded into supernovae, they spread metal throughout the galaxy. Stars get more metal enriched and more and more and more. So by studying lower metallicity environments like Small Magellanic Cloud, it's almost kind of like a time capsule that's way closer to us than you would normally expect. It allows us to look at the types of stars that would have existed in bigger galaxies like our own a longer time ago, and thus a lot further away than the SMC. Yeah, I think there are a few other things, but at least for me, those are like some of the reasons why the Magellanic Clouds are like awesome.
Great, thanks.
Well, they're pretty close, and you can resolve individual stars pretty clearly.
Yeah.
And you wouldn't go looking in globular clusters for these, of course, because they're old objects. You wouldn't find young massive stars in them.
So the TZOs that I was talking about are massive TZOs. So when a neutron star enters a massive, so greater than 8, but really greater than 15 solar mass star, there are predictions for smaller Thorn-Zikov objects that happen because of dynamical mergers in globular clusters, because there are such dense environments. You could get a neutron star hitting into another star within a globular cluster. Unfortunately, because the energy generation in those is completely different than in massive Thorn-Zikov objects, we're really not sure if there's any solid identifiers like the spectroscopy for these lower mass Thorn-Zikov objects. So there could be interesting things in there, but it would be really hard to discern, unfortunately.
Yeah, I spoke too quickly. Sorry. Our core Bohr stars are actually, I think, collisions of white dwarfs. I think it's one of the ways that they're formed.
Yeah.
Then you get enough mass, and it turns back into a big envelope that fluts up. I believe that's how it goes.
Yeah.
All very cool.
Yeah. Just a quick question, Anna. Do the Magellanic Clouds galaxy, do they have black holes in the center?
They do not. So those are irregular galaxies. So they don't have the core structure with a supermassive black hole that galaxies like our own or the Andromeda Galaxy have. There are black holes in the Magellanic Clouds, but they're like stellar mass black holes. So yeah, so not supermassive ones, but smaller ones do exist there.
Oh, okay. Okay, thanks.
Thanks.
Any other questions? Anna, what was it like to, when you got your research, you started to do it, that eureka moment and said, oh my God, this is happening? I'd like to hear about that.
So it was an interesting process, and I owe this to another scientist in the field partially. So I was working through things, and I was at sort of a middle part of the analysis where I was just starting to get these plots going when I went to a conference at the Space Telescope Science Institute in Baltimore, and there I met Carolyn Doherty, who is one of the world's foremost experts on super-AGB star models. And she came up and she was looking at my poster, and we had a great conversation. And she said, looking at the variability, and it seems like, they're really cold, you should have a look at super-AGB stars and see, if maybe that's an option. And I thought, oh, okay, that's really interesting. And I had known that a massive AGB star was thought to be a possible identity for HV2112. But it was on that suggestion that I really started to look into the track of that. I talked to my supervisors about what we could do. And that's when Jim Fuller, who is one of my collaborators, who is like a MESA expert, came up with the idea of making this pseudo-stellar model that you could use for both AGBs and red supergiants to actually get a proper constraint. And then when that happened and I made the first version of this plot, that was when I was like, oh my God, these are not what I thought they were.
Okay, any more questions? I think you got everybody amazed.
Yeah, I mean,
No.
this plot you're showing right now, that really is quite cool. So
Very definitive.
yeah,
Thank you. Yeah.
Good.
This was, yeah, I'm quite proud of how this plot came out. And yeah, when I showed this around, that was when we were all collectively like, okay, we need to, that was when we realized that we needed to change the name of the paper, because the original draft, it was just talking about Thornicov objects. And we were like, okay, we should probably change that now.
Yeah, no, we're all pretty proud of you. It's coming from our space.
Yes, absolutely. And I wanted to thank you all again, both for this invitation and the previous invitation and the invitation when I was, when I talked to you about my high school science fair projects back in the day, because all of those were really important experiences for me. You know, doing research is one thing, being able to communicate it is another, and having the opportunity to share it with other people is really important. So yeah, I want to thank the center again. You guys are just really awesome, and I'm absolutely thrilled to talk to you about this stuff.
Share anytime you want to.
Yeah, thank you.
yep, thanks.
Okay. Wow. Now I'm sort of starstruck here, excuse the expression. Not too often I get tongue-tied, but just so interesting to see how your last talk, how you were talking about TOO, and I had gone down, and that was one of the things when I was down in Australia. I wanted to see this possible star, and then you talked about it. And now all of a sudden your research has come on, and you've created a whole new aspect. And then when you talked about using the dragonflies before, I'm thinking, man, you are really on the edge, right? We, you know, out here we usually get people who talk. They've already done the whole circuit and we're at the end, but you're showing us things that are happening right now. So as you can see, I'm just gone off my mind again, babbling along.
Thank you.
Anyway, thank you very much for the great talk. Randy, where are we going to go from there? Excellent job, by the way.
Thank you.
Randy,
Sorry. Observations and photos
observations and photos. Oh, that's me.
and drawings.
Okay, let me share my page here. Mike, are you there?
Yes.
Okay, you're up.
Okay, so this one is the Leo triplet, and that's from March 20th. There was a little bit of a moon out that night, and it was pretty cold. And so the three objects there, the one at the bottom is the NGC 3628. I think that's also called the Hamburger Galaxy. And the two at the top, the one on the left is M65 and the one on the right is M66. And so this is using my ED80 and a Canon SL2. It's 40 20-second exposures. And I'm kind of limited. I've only got kind of a male slot, especially when there's snow in the backyard. So I can only look pretty much along the north-south line. So that was what was there that night. So that's what I can say about that one. We've seen the Leo triplet lots of times, but I always enjoy having a look at it.
One of my favorites too. And actually, supernovas have a tendency to show up in these two.
I need a, yep. So this is M67, same night. It's a little bit west of that. It's in, it's an open cluster in Cancer. And this was 9 15-second exposures. And I like open clusters. And it's for me, that's a nice sized one for my telescope. I can, it sort of fits in nicely. And again, it was in my mail slot. And so the next one, I guess, is, so I was expecting there'll be a few of these. This is the yellow bar there is pointing to a nova, which is now called V1405 Cassiopeia. It's kind of to the north, I guess, of Cassiopeia. If you follow the bottom arm of Cassiopeia, the thing at the top is M52, and over at the right, up, no, not the smudge there. You can just see the beginnings of the bubble nebula. Yeah, right there. So this nova was discovered by Yuji Nakamura on March 18th, and a bunch of us started taking pictures of it. So I did pictures on the 21st, 22nd, and 23rd, and then it was cloudy for a while. And this is at the end of the month on the 31st. And I can't look at it anymore because it's now moved out of my, it's moved behind a house near me, but maybe somebody tonight can see if it still looks like that. It didn't change much over the first couple weeks. So that's kind of what I can say about that one.
Nice catch, Mike. Thanks very much. Thanks for the actual pictures. Seeing that we've had rain since April. Holy Moses, I'm surprised.
Yeah, not much in April.
Okay. I think Robert got something to say, Robert?
No. I was just saying, commenting, or not commenting, but agreeing with what you said about the no sky since who knows when.
Are you there, Jim? All right. So we had, there's the heart and soul. I think it's done in the using the Hubble platelet. He didn't give me any details, so I
just enjoy.
Just enjoy.
It looks very calendarish,
to
doesn't
enjoy.
it?
Yes, it does. I think you could make the RASC calendar. And this one here, the
13-hour exposure, Jim said.
North American Nebula.
Oh, wow.
Pelican.
Is somebody checking the chat?
Yep.
Yep.
Okay, there's like
3 to 4 hours exposure.
Wow.
How about this one, Jim? The North American Nebula. We got Florida here, Gulf, everything. The Pelican is over here, right? This is the Pelican. The eye. No. Is that Great Britain? I'm just pushing my luck there. How about Newfoundland right there? I've never seen Newfoundland in the picture.
Stretching a bit.
Yeah, well, oh, you guys can see hearts and souls and pelicans. I can see Newfoundland, and I can see Great Britain.
There you go.
There's Florida. Has he? I'm not getting any on the chat. Anybody?
Hey, Jim says that Samyang 135 lens with ZWO 1600 millimeter camera.
Oh wow.
Narrowband, hydrogen, alpha, sulfur, and oxygen, I believe.
He must be biting his tongue, not being able to speak. We'll forgive you this time, Jim.
Correct.
He's waiting his phone.
Anyway,
I can't believe 13 hours.
I haven't got the patience for 13 hours, and that's just the exposure. We're not talking about how long he was on
Neither
the.
can I.
Okay. That's all we have for pictures. People donated pictures, like or seen any characters or anything. Well, let's face it. I mean, geez, this is the first night. I figured we would have nobody Here, everybody be out trying to get their telescopes out after the thirst.
It's dark now.
Anyway, Randy, if you're not looking at Venus for me,
Yes, sir.
Nikolai next.
Yes, we have Nikolai in the sky this month.
You ready, Nick?
Yes, hello, can you hear me?
Yes.
Yep.
Awesome. All right, before I tell you what's up in the sky, as the observing director for the center, I wanted to take a moment to congratulate Susan Hart, who is on this call right now. Hi, Sue. She recently completed the requirements for explore the moon with binoculars certificate that is hosted by RASC National. So congratulations, Sue.
Congratulations.
Thank you.
Sue, have you received your certificate yet?
I have, yes, and the little pin to go with it. So yes, I'm planning on getting it framed.
Perfect.
Yeah.
Could I put you on the spot and have you tell us how it went, how long it took you to do that? Was it fun? Was it annoying? What was it like?
Well, I did write a little piece for Randy. I think there's some kind of newsletter coming out. Is that right, Randy?
Yes, that's right. Yeah, you have an article.
Just summing it up, I guess. Yeah, it was fun, but it took me a long time, mainly because I didn't really do much observing last summer for various reasons. But yeah, when I started again in the fall, I had my fancy new binoculars, so it made it a lot easier, much more enjoyable. And yeah, and I mean, I thank Nikolai and Randy there for reviewing what were, I think in some cases, not very legible notes, but I did try to organize it in summary. But yeah, no, I learned a lot, definitely learned a lot. And I'm now doing Explore the Universe program. And I've got through, of course, I've done the moon bit quite quickly. And I completed the constellation and bright star section too. The very last clear light we had, I was out for a long time and I did that. So I don't know now about the dark sky objects. I'm not sure how successful I'm going to be with my binoculars, but anyway, I'll go for it.
That's great. I'm glad to hear you enjoyed it and that you're working on your next one. I am quickly going to share my screen and show everybody where to find the programs with RASC. So here it is. Can you see my screen?
Yep, I can.
Okay, so this is rasc.ca. That's the RASC National website. If you go under Observing, then Observing Programs. And here are the observing programs on the left. And if you click on each one, it will tell you what you have to do in order to complete them and get your certificate. And in some cases, you get a pin as well. So highly recommend. You learn tons just by doing it.
Yeah, it's really interesting. And the RASC site is very useful too. They've got lots of things there that you know, and with Explore the Universe, I've also bought a book called Night Watch, which I found really, really good. So yeah, no, it's definitely worth doing.
Well, if anybody has any questions, feel free to talk to Sue.
Well, I think John did it, didn't he? John Peddle did it with telescope. I think he's.
Yes.
Oh no, I think he's done both. Explore the Universe and Explore the Moon. Yeah.
Nikolai, if you could just click on the e-store for a second, you can. There's actually a couple of new books there. Sorry, John, I'll get you back in a second. On the certificate programs right there. So.
Right. Yes. Yeah.
Sorry, John. I think I cut you off.
Oh, that's fine. Yeah, I did Explore the Universe 2 years ago, and I finished Explore the Moon there not too long ago. Explore the Moon with the telescope.
Yes. Yeah.
And it is a lot of fun, I have to say.
It is. Yeah. Yeah.
Well, that's great. Hope to see more people doing these, and you know, I'll be very excited to present who the next I get not winner, but recipient of of an observing certificate is. So definitely check those out.
Yeah.
All right.
Thanks, Nikolai.
Yep. Thank you. So let me unshare and quickly ask about Venus, which is the observing challenge that I posed to you last month. I have a pretty good idea of what the answer will be, because as fate would have it, meteorological data shows that we have not had any clear nights, at least not in the last 3 weeks, which is, when Venus would have been observable, except for tonight. So unless I'm wrong, and unless somebody actually went and tried to see it during this meeting, I don't think that anybody would have seen Venus as it emerged from its superior conjunction with the sun recently. So has anybody seen Venus?
Randy?
I think tonight is actually the first night that there'd be enough separation for you to actually see it. And then it's going to be a challenge. Gets better as the nights go on.
Yes, unless I guess you try to observe it during the day, which is a challenging activity.
I've done it.
Something in the chat. Yes, that rule is very true. I actually agree with that completely. All right, so let me share my screen again then and talk about what's in the sky this month. All right, share. Can everybody see this? Yes, okay. So as always, this is uploaded to our website if you need to reference it. We do have sun-related phenomena for today, sunrise being around 6 a.m., sunset being around 8 p.m. So that's for today, and the day continues to grow as we approach summer solstice. Here is some information on planets, rise and set time, and here is a picture of the sun taken yesterday. This is actually the most active the sun has been in a long time. We do have 3, fairly significant sunspot groups visible at one time right now, with one, rotating closer to the center. Again, seeing the sun has been a challenge, so actually tomorrow will be a good opportunity again. If you can have a look, certainly do, and of course always use proper filter when you do that. Now moving on to planets, Mercury is an evening planet right now, or it will become one into May, and it will actually undergo a very favorable evening apparition during May, meaning that it will be well separated from the sun, and it reaches greatest elongation on May 17th. So definitely have a look at Mercury. And here comes the next observing challenge. Since everybody did such a poor job at seeing Venus, I'm giving you a challenge to see Mercury, and kind of as a substitute to this month's challenge. This time though, you have to see Mercury and the Pleiades together. There will be an approximately 3-day period centered around May 3rd, where Mercury and the Pleiades will be very close to each other. Of course, if Mercury is visible, it means that it's going to be twilight. It's not going to be complete darkness. So it's challenge. So just look low in the west-northwest shortly after sunset for that. Pleiades are generally pretty easy to spot in twilight. Just use binoculars. That will be the best thing to use for that. So please try to see that and let me know next time if you were successful. If you only spot Mercury or only spot the Pleiades, you get half points. You get full points for spotting both with the same field of view. Venus returns to being a bright evening star. As I said, it underwent superior solar conjunction late March, and so now it becomes a bright evening star as rises higher and higher as we move into May. Mars continues to be an evening planet and Gemini through May. It is too far from Earth and thus too small to resolve much detail. Morning planets, we've got Jupiter and Saturn remaining close together. They rise about 3 hours before the sun, and that allows them to climb high enough for somewhat meaningful observations early morning. Planets that are not visible right now are the ice giants, Uranus and Neptune. Comets, here's the list of the brightest comets. Nothing worth talking about at this point. Asteroids, here are the 5 brightest asteroids. Here is a link for the latest supernovae. Last I checked, nothing worth discussing. Meteor showers, we have 2 coming up over the next month. I'll mention that in the calendar. And we do have the top deep sky objects listed here as well. So some of my favorites here, as we go into May, are the Whirlpool Galaxy and also the Sombrero Galaxy. Stunning visual objects, just with a small telescope. Highly recommend checking them out. ISS passes listed here, lots and lots as we go into May. And here are the observing calendars. Still no observing sessions. Can't come soon enough. Yeah, the next meteor shower, they're very minor meteor showers. There's one on the 22nd, which is tomorrow night, and then there's another one on May the 4th. I think that's it. Does anybody have any comments or any questions about anything that I talked about? No.
Meteor shower tonight after midnight is the peak.
It's actually tonight?
Yeah, it's after 12 o'clock tonight will be a good time to if the sky's clear.
So that's the Lyrid.
Yeah.
10 per hour. That's the average.
You gotta go south to get a good one.
Yeah.
The south guys get a higher rating than us.
Yes.
So that's about 2 or 3 in actual viewing. Okay. It's still a meteor shower. And I love meteor showers. Okay. Thanks, Nikolai.
Yeah.
Any questions for Nikolai? Anybody got anything that he might have missed that you might think might be interesting to someone to watch in the upcoming time? Oh, well, we'll switch back to Randy, I guess.
Okay.
Next on our list, Randy, you got something about?
I just wanted to mention we have another speaker next month. Jim Johnson is going to talk with his contact about his satellite project. Also wanted to mention as the last call for newsletter items. Still got a little bit of time to get them in. They'll be publishing fairly soon. I wanted to give you a heads up that the RESC AGM is coming up on June 25th. I assume there will be some Zoom type stuff coming out on that fairly soon. Also wanted to mention right on the front page of the RESC website, there's a calendar, and that has a lot of certainly the central meetings and lectures and stuff. So give that a look if you haven't had a look at it. And that's all I have.
And Anna, there'll be a small token from us delivered to your house, right, Randy?
Oh, thank you so much. Thank you.
How long are you going to be in town? For a while?
Yeah,
Okay.
at least until the middle of May, but probably until the beginning
Okay.
of June. So
Canada Post is quicker than that, just barely.
thank you.
Okay.
I hope you get a chance to use that scope that's in the background, Anna.
I mean, I always have this after I talk to you all. You all inspire me with your amazing photos and your love of the sky, and you were talking about Venus. So yeah, once you're done here, that's going outside and I'm gonna try and take a look.
Yuri.
No, tonight would have been the first opportunity, and you need a perfect low unobstructed view to the west. So it's
I'm up on top of Signal Hill would be a good place.
yeah, that would be the place.
I don't know if you catch the Pleiades because of the light pollution, but certainly should be able to see Venus. Or yeah, with the low horizon. Well, I don't know. Kenmount Hill might be in the way. I'm not sure.
Oh no, Signal Hill's a great place.
Oh, yeah.
Yeah, should be a good spot for that.
Yeah. See you up there, Phil.
Yeah, some of us live at the East End. So.
Socially distanced, of course, right?
Yeah. Okay. Is that everything we got for the meeting tonight? Any?
Yeah, I guess it's not too early to mention. We're still hopeful of some kind of a socially distanced video, whatever, sunrise solar eclipse, June the 10th. I'm doing what I can to make that happen. We'll see.
Well, I'll give you an opportunity to chit chat between each other. Anybody want to say anything? Anybody who's done anything? Oh, how did your night, geez, April 10th night,
Yuri night.
first man in space?
Went super well. There was both the global event on the Saturday, April 10th that you mentioned.
Yeah.
They had planned for, I think, like just over 3 hours of content. They went on until 4 hours, and people in the backstage were there till like 5 a.m.
Wow.
So that went really well. And then there was the Canada event that I was co-hosting the Monday night on April 12th itself, and that went super well. My co-host and I are so proud of ourselves. And we had a great lineup. We had someone talking about Canada. We had someone talking about black holes. We had Bob Thirsk there. We got a shout out from Chris Hadfield. We also had someone talking about James Webb Telescope. And we had Matt Russo doing sonifications, who also performed for us, which is really cool. So if anyone's interested, it's still online on YouTube. You can YouTube Yuri's Night Canada, or I can provide a link. Yeah, it went really well. So thanks for asking.
Can you put the link in the chat for us?
For sure. Yeah, I'll just
Greatly appreciate it for those people who didn't, who forgot or didn't have the time. Type of thing.
I can put both. They're both on YouTube.
Okay, greatly appreciate that.
Yeah, no problem.
No problems with the broadcasting of you were using Backyard, was it?
Yeah, we were using StreamYard.
StreamYard.
No, it was pretty smooth. A few little like glitches with just like choosing the screen type to use, but it's what happens in a live show, of course. But yeah, we had a lot of fun, and we were able to successfully do our soft launch for Canada Moon. So that was also exciting. It's becoming more real now.
Good.
And we're still headed for July 1st launch date for being able to accept submissions for it. So
oh, excellent.
Keep posted on our social media and website, Canada2Moon and CanadaMoon.com, which I can put that in the chat as well.
Yeah, put them on the chat too, please. Greatly appreciate it.
Sure, no problem.
Okay. Anybody doing any observing? Anybody see the helicopter fly on another planet? That 8 seconds going up and down.
I like the digital altimeter. 0 meters, 3 meters, 0 meters.
It looked like it came down faster than it went up, because it seemed to bounce once it hit.
Well, they were worried they'd never get it off there for a while. had to reprogram it, didn't they? And they thought the dust wouldn't charge because of the dust on the solar panels. I see my friend Paul Mason is still doing images of Mars. Less than 5 now, and you can actually still see detail on. Quite surprised. I can remember at 8 arcs, that was it for visual, and 6 was for real film. But digital has really made it get much smaller, so much detail.
Jim Johnson points out that SpaceX's latest grain silo launch with a static fire for it, the Starship, the SN-15, is going to happen tomorrow.
Yeah.
And they're going to try and launch that thing Friday or Saturday, and maybe it'll land this time.
Yeah, the crew launches delay the day till Friday, right?
Yeah.
What a quiet bunch tonight. I can't believe. Gee,
Everybody's
usually can't-
itching. to see
Usually I
me.
got to press mute. I guess you're all just tired out of being rained out every night, every day. And
I'm just waiting to use that.
I think they're all looking at the window.
I got all my things set
Our
up,
feed
so.
froze up for a couple minutes right at 9, but just came back.
So, nobody else besides Susan doing any of the oh, gee.
Certificates.
Yeah, certificates. Thank you. Fill in the blanks. I think I'm suffering from not getting out and getting some fresh air. I'll get my shot on Friday, so maybe
Good.
that will make me feel happier.
Oh my.
Well, it's a beautiful sundown yet here in London, so cleared off nicely. So I'll get out in a little bit and take a look.
No snow today.
What, for us? Yeah, we had snow this morning
Yeah, snow
throughout the
in
day.
Ottawa at the moment, isn't there?
Yeah.
So,
Toronto got 3 centimeters.
oh, that's enough to stop the city.
All right. I guess we'll end this meeting. Thanks for all for coming. Anybody got anything else to say? Hopefully clear skies. Hopefully you all get better. You all get your shots soon. And maybe sometime we'll actually see each other.
Yeah. Get out observing.
Yeah,
Absolutely.
More than good.
I'll be out observing in about 10 minutes once I turn you
Yep.
guys off.
Yeah.
Good night. God bless. Whatever
Good
they
night.
say. Clear
Yeah.
Thank you,
skies.
everybody.
Bye.
Good night, everybody.
Anna.
Thanks,
Thank
Anna.
you.
Thanks, Anna.
Thank you.
Thanks.
Thank you.
Great talk, Anna.